Exercise 1727 is asking you to predict the products for some sigmatropic rearrangements. There are only two sigmatropic rearrangements that you need to know for this test, and they are both 3-3 sigmatropic rearrangements. The first one is the Cope rearrangement, and the second one is the Claisen rearrangement. So the Cope rearrangement is a 3-3 sigmatropic rearrangement, and it's all carbons in the ring. The Claisen rearrangement is also a 3-3 sigmatropic rearrangement, but one of the atoms in the ring is an oxygen. You'll recognize a Claisen rearrangement because you will have that rearrangement anywhere where you have an allylic, vinylic ether. So an allylic ether is an ether that's one atom away from an atom in a double bond. So here the ether is attached to an atom that's one atom away from an atom in a double bond, so that is allylic. And vinylic means that it's directly attached to an atom in a double bond. So anytime you have this pattern in allylic vinylic ether, you will have this Claisen rearrangement, which means there are going to be three atoms from where a new sigma bond is formed to where an old sigma bond is broken. And then for the Claisen rearrangement, you'll recognize that because you'll have two carbons between two pi bonds. So these might be a little easier to see just by doing some practice. So allylic vinylic ether Claisen rearrangement. Just keep that in mind. So what we have here, we see that we have an ether. It's an oxygen with carbons on both sides. On one side, it's directly attached to a carbon in a double bond. That's vinylic. On the other side, it's attached one atom away from an atom in a double bond. That's allylic. So here we have an allylic vinylic ether, and that means that we're going to have that 3-3 sigmatropic rearrangement. So count from the end of the allylic double bond, so that's 1, 2, 3, and then count the three atoms, including the oxygen, on the vinylic double bond. So that's 1, 2, 3. So that's our 3-3 sigmatropic rearrangement. We're going to be getting rid of the sigma bond between the two threes, and we're going to be adding in a sigma bond between the two ones. So we'll copy that molecule. We're going to have a new sigma bond here, and in order to form all of these things, we will make all of these electrons move around in a ring. So I'm going to have them move clockwise. So this bond will go down, this bond will go over, this bond will go over. And just so we can follow these a little bit more easily, those electrons, I'm going to color them. So we will have those blue electrons going over to create a sigma bond. We have the three carbons on top. So if we're numbering these, this is 1, 2, and 3 on top, 1, 2, and 3 on the bottom. That 3 was the oxygen. So the blue electrons moved over to create that new sigma bond. The orange electrons move over to create a new pi bond. And the purple electrons move over to create a new pi bond as well. And so that is our product. Let me move this oxygen up just a little bit. So there you have it. So that would be the product of that Claisen rearrangement. Oh, and on carbon number 3, we still have those 2 methyl groups. So that would be the product of that Claisen rearrangement. So in this one, you notice you have 2 pi bonds, and in between them you have 2 carbons. So that is a sign that you have the Cope rearrangement. So in between those double bonds, so count from the double bonds. So here we'll have 1, 2, 3 carbons. From the other double bond, 1, 2, 3 carbons. We are going to be getting rid of the bond between the carbons 3 and 3, and we're going to be creating a new bond between the 2 number 1 carbons. So to do that, we will move all of these pi bonds in a ring. I'm going to go clockwise, or all of these bonds here in a ring. And let me color these so it's easier for us to follow. So first we'll just copy the geometry. We'll see how things turn out. We have this bond going up. The purple bond is going to join that one. We have this bond going down. The orange electrons there move to form a new sigma bond. We have this sigma bond there, but the yellow electrons won't be there. Those will be forming a bond, the pi bond, between those 2 carbons. So if we were numbering this again, we would have 1, 2, 3 at the top, 1, 2, 3 at the bottom. And notice that ultimately we formed a bigger ring. So there's not only those 3 carbons, but there's an extra 2. That means we have a total of 8 carbons in this ring. And so if we draw them with the proper angles in between them, we'd be drawing an 8-carbon ring. So that would look like this, sort of like a stop sign. And we can number these. We can number this ring all the way around. So we can go from 1, 2, 3, 4, 5, 6, 7, 8. This is just to keep track of stuff. If we do the same thing in this larger ring where the angles are drawn more appropriately, you can see that we have that purple pi bond between carbon 2 and 3, and we have a yellow pi bond between carbon 6 and 7. And so that would be the product for that Cope rearrangement. And the rearrangement is happening because of the p orbitals here twisting over and overlapping in phase. So here we have 2 carbon pi bonds separated by 2 carbons. So that is a sign, again, of the Cope rearrangement, 2 carbons between 2 pi bonds. So that's a 3-3 rearrangement. So start on one end of the pi bonds, 1, 2, 3. And then start on the other end of the pi bonds, so 1, 2, 3. And so we are going to be getting rid of the bond between 3 and 3, and we'll be adding a sigma bond between 1 and 1. So I'll draw in the electrons here that we're going to move in different colors. Oops, so that's what we had. And now we can just move those around in a clockwise ring. And the product that we'll get this orange bond will now go here. The purple bond is going to go across. we'll still have that black bond going down, and then we have the ring. The yellow pi bond will go down here, and that is our product for that rearrangement. And that's the cope rearrangement, because we don't have an oxygen. It's a 3-3 sigmatropic rearrangement. We've changed the position of a sigma bond, so it's sigmatropic. 3-3 sigmatropic rearrangement with all carbons in the ring where the electrons move in. So that's the cope rearrangement. Now in this next one, in D, which is the last one of these rearrangement exercises, in D we have an ether. So an oxygen with 2 carbons on either side. Now on one side it's attached directly to a double bond, which means it's vinylic on that side. On the other side, it's not attached directly to a double bond, but it's just 1 atom away. So that means it's allylic. So here we have an allylic vinylic ether. That's a sign that we have this cope rearrangement. Now for the cope rearrangement to work, the 2 pi bonds kind of have to line up a little bit. So it's going to be a little easier for us if we number this. We want to redraw the molecule so the 2 3s are pointing at each other. So here we've got the 1, 2, and 3. Oops. And so we want them to kind of go in the same direction. We know they're going to form a sort of 6-membered ring. So this is going to be carbon 1, and then 2, and then 3. Now notice off of carbon 1 we need these 2 methyl groups. So 2 methyl groups. Off of carbon 2 we have another methyl group. And then between carbons 2 and 3 we have this pi bond. So that's drawing that same molecule with the sigma bonds twisted so that we can sort of get a better sense of how this Claisen rearrangement is going to happen. We know it's a Claisen rearrangement because we have a allylic vinylic ether. So we're going to form a new bond between the 3s, and we're going to break the sigma bond between the carbon 1s. So let me draw those in. Those electrons that are going to move around in different colors so we can track how they move. So those are the bonds that are going to move around, and then here I'm going to move everything clockwise. So this sigma bond is going to break. It's going to go right over there. The purple bond is going to break. It's going to go over here. And then the pi electrons, those yellow pi electrons will move over too. So let's take this. Purple electrons are going to move over. So they're going to form a sigma bond here. The yellow pi electrons are going to move over. So they'll form a new pi bond here. And those orange electrons are going to move over and form a pi bond here. And so that for me would be fine, perfectly fine, as the answer for this rearrangement. Now technically this will probably change because you've taken away a very special feature of this ring, which is that it was aromatic. You had overlapping parallel p orbitals all the way around the ring. In the starting material, that's a very stable arrangement, and that's not there in the product that we predict here. So this would undergo further changes. But if you can draw this one product, that's perfectly fine for me to make sure that you see that when you have an allylic vinylic ether, you get this Claisen rearrangement, this 3-3 sigmatropic rearrangement with an oxygen in the ring that you're working.